Thank you very much. Thank you all for coming, and congratulations to ITCS for 10 successful years. I'm hearing a bit of an echo. I don't know if it's bothering anybody else. If it's not, I'll try to filter it out. Okay. So this is a talk that I usually give over a 1 hour period, and I had to compress it today to make it 25 minutes. The audience is also quite different from the one that I'm usually used to. And as a combination of these, compression and the uncertainty, probably you won't understand something in the talk, but if so, that's a good thing because it explains the importance of why we should think about communication with uncertainty. I mean, and that's exactly the kind of questions that I'm going to model. How do we try to react to an unknown audience and try to tell them something that is potentially useful and interesting to them, and how to build a mathematical model which tries to capture settings like this. I don't want to waste all your time trying to tell you about all the physics, the math that you already know. I definitely don't want to teach you English, but I can't count on very many specific aspects of these things. How can I try to leverage what I think you know without it leading to major confusion? One thing that will help is actually you also working actively over here. So in fact, this will be one of the messages in the talk, but at the end, if things are not really clear, please do ask questions. The whole idea is to set the problem up, not how to solve it, and that's where we are going to head towards. Now, I'm trying to model some things like human conversations, and human conversations involve two ingredients, our ability to think and our ability to speak and listen. And there are two different theories which have talked about these two aspects. And these are both very famous. And in fact, I was not here for all of yesterday. I was here for just the last two talks. And already there, I saw exactly these two pictures. So it's not probably completely unfamiliar to all of you. Turing and his work, though I'm talking about his 1936 paper on which led to the theory of computing, and Shannon in his 1948 seminal paper on communication theory introduced us some very basic concepts that we have to work around. I'll try to build on these theories, but then I'll also want to, in this slide, I want to highlight one gap between the theories. Theory of computing really relies on the fundamental principle, which is universality. And universality really means you don't have to design a computer for a particular task. A computer will solve any task once you've designed it. And you can program your computer to look like any other computer that you would have wished to build. You can program your computer to do whatever you want to do. The communication principle, on the other hand, that Shannon revolved around was you should design your communication architecture very carefully. Sender should figure out how to send messages. Receiver should figure out how to decode the messages. And this is the overarching principle behind the internet today, and everything is designed very carefully, centrally. And as long as the sender and receiver are synchronized, they can communicate correctly. But when that implies that you should not program your device. So clearly, the bottom lines in the two theories are somewhat contradictory. So how do you talk about human conversations which somehow lie in the interface of the two? Humans do think, they do communicate. Should they be trying to be reactive or should they not? And similarly, the next generation of computing devices, should they try to use their computing power to help them communicate better, or should they suppress it so that they can communicate better? What's the right mechanism? So I do want to talk a little bit about the behavior of intelligent systems. This is something that the theories of Turing and Shannon have given us a powerful ability to model and manipulate. And here we are talking about intelligent systems, which humans are computers. I'm not very committed to any one version of this talk. And the aspects that I want to talk about are, intelligent systems go around acquiring knowledge, they process it to get further inferences and reasoning, and then they communicate and disseminate. And if it wasn't for the fact that we were a society, we wouldn't be as far advanced today in terms of our knowledge if we were trying to work it all out by ourselves. So it's definitely the communication, the social networking plays a significant role in our ability to assimilate this knowledge. And we do want to build mathematical models which try to capture that. Theories of Turing and Shannon can help us, but how? That's the question. And one thing that I do want to talk about in the modeling is, when we start probing the limits of systems, And when you've made very few axioms, you may not get a very good model of what humans can or cannot do, uh, or at least you may not have a very perfect model of what they can do, but you definitely get upper bounds on what they can do. So the limits, no matter what, will also apply to human behavior, even if we haven't captured human behavior very accurately. So this is making it pretty important to study. Now, most of this talk is about communication, and one fundamental concept that I want to keep hovering around is the concept of entropy, which was a very key contribution in the Shannon theory. So, of course, if you look at it in the literature, entropy was not introduced for the first time in this paper. The thermodynamics concept of entropy always existed. Von Neumann actually had in his treatise on quantum mechanics definition of the entropy of a quantum system, quantum state, which pretty much is a generalization of Shannon's notion of entropy, which appeared a dozen years later. Okay, so Shannon's notion, however, ended up having profound impact, okay, despite the fact that it's a special case of a concept that's already existing in the literature. What makes it so special and so profound? One thing that I think made the Shannon definition of entropy, and by the way, the formula is here, but specifics are not too important to us. One reason that the Shannon notion had such profound effect on it was an abstract concept. For the first time, we were detaching the principle of entropy from the physics. It was not the entropy of any physical system necessarily, it was just an entropy of an abstract quantity, a random variable. That made this a very interesting aspect. By the way, if you haven't read about some of the developments over here in any professional setting before, then maybe you can pick up this pop science book called Information by James Click, which gives us a tour of the development of the machinery and the mathematics of information theory in a very accessible form. So I'd encourage you all to go take a look at it at some point. Now, the one reason that Shannon's work gave us very profound, really helped us register the concept of entropy was he gave it a very operational view, this particular concept. What was this operational view? It said that if I have a random variable and I want to send it to you, the entropy is the key quantity which determines how long the communication is. Let me describe this a little bit carefully and precisely over here. I have a random message that I want to send to you. The message is denoted by the letter M. Or Alice and Bob, in this case, are the two players. Alice has the message M, and Alice and Bob know the distribution from which this message is going to be chosen. The message is going to be the integer 1 with some probability, integer 2 with some probability, integer 3 with some probability, etc., etc., etc. This probability distribution is completely known to Alice and Bob. Alice is the sender of this information. Bob is the intended receiver. Alice is asked to communicate M to Bob, but she doesn't have to send the integer in some vanilla. She doesn't have to send the binary encoding of M necessarily. Maybe she should try to compress this message because it's not very likely to take on certain values. Maybe I have a random prime number between 1 and n. Maybe I have a random square free number between 1 and n, etc. Depending on what I know about the distribution of this message, maybe different mechanisms of expressing this integer will be more efficient. What is the mechanism which will be most succinct in terms of the expected length of the communication? I hope this mechanism is, this definition of a problem is very clear. This is a concept. Compression problem is something that I will keep talking about in this talk. All right. The theorem due to Shannon, and with the optimal version of this theorem coming from from Huffman, is that the answer is entropy. The expected length of the communication is sandwiched between the entropy of this distribution P and entropy plus 1. 1 bit is the maximum deviation that we have, and this a mechanism for how to transmit information like this was given by Shannon. And this concept started to play a key role in the development of the technology of communication. So most of our ability to communicate information over the internet, over the uh, airwaves that we've developed today, revolve around our ability to use the medium that's available to us most efficiently. The most efficient used should take us down to the entropy of the information. Okay? So that has been our challenge and our success in this technology so far. But Shannon was already trying to apply this information beyond the technology to which we wanted to apply it. He also even tried to think about, and by the way, what does this have to do with human communication and languages? And he was trying to develop a probabilistic model for what may language already be all about. And one of those was this series of approximations. I'm quoting from his paper over here. He described a series of approximations a natural language via very simple languages. None of these is going to be perfect, but maybe as the limit goes to infinity, start getting something closer and closer. The ith order for any integer I, you can define an ith order approximation to language. The ith order letter approximation would say, given a sequence of I minus 1 symbols that have last appeared, what's the distribution of the ith letter looking like? You can perform this analysis empirically for English. You pick up a text and start computing these probabilities. And now you can say, what kinds of sequences do I generate when I just apply this probabilistic model? What do I get? Shannon actually in 1948 in this paper did this experiment. Just to explain, those days we didn't have computers, we didn't have random number generators. He actually worked with a table of random numbers. He had computed the probabilities empirically from some piece of text, I don't know which one, and then he actually applied this random process to it. It was a very non-trivial exercise. He even says in the paper that he got tired of it after a little while. But let's see what's the third order letter approximation. I don't think I'll try to read the sentence. It doesn't really make much sense, but not too bad. I mean, there are, when you look at it kind of very, very locally, plausibly, like we were thinking of English. It doesn't look French. Might have been Latin, I don't know. He also sort of decided that after maybe fourth or fifth order I think after fourth order letter approximation, definitely got tired, and then moved to word approximations where you say I build a model which says if I take the first I words, I minus 1 words, what's the distribution of the ith word, and let me generate according to that. That, of course, not too surprisingly, is a lot more reasonable. And it says, now you can even read it, the head-end in frontal attack on an English writer. I mean, if I gave this as a reading exercise in maybe grade 9, people would just read the sentence and fine with it. I don't know. Well, he didn't prove any theorems about it, but he did make this observation empirically that, look, actually, even though when I'm building ith letter approximations or ith word approximations, it actually seems reasonable for about twice the length that the approximation was designed for. So there is some lack of entropy in English. There is some, it's not completely wild. It's not that I'm getting very meaningful sentences, but there is something significantly more restrictive. And so probably entropy of English is a concept that makes sense. Maybe I can produce upper bounds on the entropy of English, and having done so, use it to compress text. And we have been very successfully compressing text. And the Lempel-Ziv algorithm, etc., for compressing text, in principle, rely on this kind of a modeling. They came up with this modeling to, suggest the algorithm, and then proofs or analyses of these algorithms also rely on such models, and say on such models it actually does well. So entropy does seem to capture natural communication and natural language, but does it really do so? And that's the kind of a question that I want to talk about more today. It would appear if, it would be a reasonable thing to say if you could somehow say that, well, natural language is really given by a distribution on possible messages that I want to send. Maybe for this talk, I have a mental image of what are the possible messages that I could send. From this distribution, I'm compressing, which tells me how to express it in words, and then I express those words. So language could be a collection of messages that we may wish to send each other and a probability distribution over these messages. And then the dictionary should tell me how to convert messages into words or a sequence of words or a sentence or a paragraph or an email, etc., etc., etc. And that's possibly one way to interpret language. And that would, if that were correct, then we would really say, well, the optimal way of expressing things would be to pick the optimal compression mechanism for this distribution, apply it, you would be extremely efficient in your communication. Now, the thing that we see in languages is none of this features of this optimal compression. It is not optimal, but it's not even, it's not unambiguous. You have words which could mean multiple things. You have multiple words which could mean the same thing. Inefficient, it's ambiguous. Everything happens in language. Where are we getting all of this from? This is kind of things that we want to get to. And why do we get there is that real world, language is not really just, a sequence of messages. It's sort of messages given under a given context. So today we came into this room and we all assumed some knowledge of English, some knowledge of mathematics, some knowledge of set theoretic notation, which I'm actually relying on pretty heavily whenever I even put, h of p. That's some notation that makes, that assumes some common context. We rely on this context, and language really tells us what kind of a distribution on messages should you expect given a context. And given that context, how should you actually translate it into a given message produced under that context into a word. So it's really a simultaneous approximation for many, many, many different contexts. And it's trying to tell you for each one of these contexts and a given message, how should you express it. So this is the process, and we would like to understand what kind of optimality features can you expect over here. So we're not going to study language today, but we're going to study something which is analogous to language, and to me, compression is not analogous to language. I would like to study mechanisms which try to take messages and express them succinctly and try to say, what can I say about correctness? Will you be able to understand what it means? Can you decompress? And what's the robustness level? When I'm talking to you and I'm assuming a context, do I need to work with context being shared perfectly or not? And the challenge, of course, in the real world is context is not perfectly shared. This is where language introduces its many variations and eccentricities, but it's a remarkably good solution for the problem. We are able to eventually talk to each other from diverse communities together, and can we sort of build, extract some essences of these mechanisms and maybe port this also to computers when they're talking to each other. Now, this is part of a broader theme that I'm exploring in my research, and I welcome other people looking at it. And I have many collaborators who've joined me in this quest. And this is looking at this concept of uncertainty in communication. And this is a repeating theme in human communication for sure. There's always some uncertainties that we're trying to deal with. We did not synchronize. We do not start the day opening up the dictionary online and saying, what is the exact dictionary suggesting today? Just start our conversations. If we suddenly hear a new phrase that we've never heard before, maybe we rush to the dictionary, maybe we interact and figure it out. We do not synchronize. Computers are so far communicating with each other by synchronizing in the morning every day, update their software, and till I update that piece of software, I will not take the next step. Maybe we can overcome that hazard this way. When communication tasks come with some context, there is two distinct options. We can either ignore the context completely, and quite often you can actually achieve communication by ignoring context, but it would be the same as the ability to tell you about what my research interests are, and the success without assuming any mathematics or physics. It'll take us a very, very long time. And so when you ignore context, the tasks may be achievable, usually are in our mathematically defined problems, but you should really think of the parameters associated there as being considered extremely inefficient. We do not want to see those. You can use and assume that the context is shared perfectly But this will work only when the context is really shared perfectly. The task is achievable extremely efficiently, so we do want to leverage this context. Don't have a precise shared context. And what we would like to solve in these kinds of problems, the kind of problems that we are trying to introduce, study, and solve, are cases where the share context is being shared imperfectly, and yet we can get moderate efficiency. And we often see that these are non-trivial challenges associated with it. You cannot just take the old solution and hope it'll work. But quite often we find that there are creative alternate solutions which work. And I'll try to explain all of this in one vignette, again applied to communication, compression. I want to solve an uncertain compression problem. Take the same setting as the compression problem. Alice had a message. She wanted to send it to Bob. Alice and Bob knew a distribution. Now, Alice and Bob have two different distributions. Alice has a distribution P. Bob has a distribution Q. And Alice thinks the messages should be coming from P. Bob thinks they should be coming from Q. This is a pretty reasonable analogy to the kinds of backgrounds. I think this is the kind of English that you know. This is the kind of English you actually know. Maybe very different. Now, what does Alice want to do? She gets a message M, and she would like to send its compression. The compression is now a joint function of the message that she's got and the distribution she has in her mind. And she sends that over to the receiver, to Bob, who gets this message and now has to figure out what did it really mean. So he'll probably compute some function of the message that he received, of the word that he received, and the distribution that he had in mind. And he will come up with something. What we would like is that usually the message that he decodes to is exactly what Alice sent. And at the same time, we want to have, provided these distributions are close, there is a certain concrete measure of definition of distance between distributions that we use in this work, but it's not too important. I'll get rid of that. What they really want to do is to minimize the expected length of the communication once again. So exactly the same problem as before if P was equal to Q, but now P is really not equal to Q, they're just close. Can they still compress effectively? Now, an interesting phenomenon is that if you look at natural language, this kind of a solution to this pretty much embedded in it. Why? Every time I want to say something, language tells me a bunch of options. Here is a short way of saying it. Here is a longer way of saying it. Here is an even longer way of saying it. What we tend to do is to estimate which one of these would be right under our current situation, our current estimate on the uncertainty between me and you. And we send that message and we hope that it usually works. One can formalize that mechanism explicitly, and it's being done on this slide, but I won't read it out. And what you can prove is that indeed, if this mapping from messages to words had been somehow random, then you would have actually achieved a compression which would be exactly the entropy of this distribution, plus some penalty that you pay because of the uncertainty between me and you, but something which is very modest. Now, this is a very simple theorem to prove once you decide to set it up in this way, so it's not something that I want to elaborate on too much. It does seem to say that entropy remains operationally effective even in an uncertain universe when we are communicating like humans are, with uncertainty between sender and receiver. But this theorem should be taken with a grain of salt, because over here we had this, I injected this technical condition if this dictionary is random and the dictionaries are not random. What we would really like to say is that there even exists a dictionary which would work, and we really cannot prove this because you're using this thing, say for a particular choice of P and Q, random dictionary works. We don't have a single solution which works for all cases. So there's a big open question, mathematically extremely interesting and simple to describe, but that remains open. All right. There are other examples that we've played with in context and communication. When people are communicating, there's some randomness can often be a very useful resource in making it effective and compressed. Assuming that we don't share randomness perfectly but share correlations, can you still get similar benefits? Knowing what the goal of communication is. Why is it that I'm here talking to you today? Why is it that you're here listening to me today? This can help communication a lot. This is something that's formalized by a model due to Yao from 1980. And once again, you can say, well, what if this notion of knowing what you want to talk about is not known perfectly but imperfectly shared? Once again, we have theorems which capture this and talk about it. I'll end with this last slide here. There's a pressing need to understand human communication. There's very little, as far as I see, that really addresses this issue of the uncertainty in context. Context is a really, really big player. It's voluminous. The context for our talk today was everything we knew, and that's pretty large. It also plays a very huge role in making communication effective and small, but it's also a major source of vulnerability, ambiguities, and misunderstanding. And trying to overcome all of this is a major challenge, and I welcome people looking into it. Thank you very much.
Thank you, Madhu, for this very nice talk. We have time for questions.
Yeah.
Okay, all right, go ahead.
You're talking about beyond. What about in the alien civilization hypothetical situation?
So the question was, can you not also tell the decoder how to receive? In many of these cases, for example, let's apply the concrete case of compression. I want to send you the message, and I also want to tell you this is it's roughly equivalent to saying I want to tell you this is the distribution that I'm using. If the distribution is an arbitrary distribution on a universe of all possible messages, this is just too much. It's way overkill. It's much more inefficient than just assuming some vanilla uniform distribution and compressing according to that. So quite often, I think we are trying to think about cases where the context is so huge that trying to resolve the context is an impossibly inefficient solution. Ignoring context would be simpler, but even that we don't want to do. We want to leverage the context and get faster.
There are two parts in my question. As I perceived in the way you talked, there was an element of super dense coding. So basically, we consider Alice and Bob if they have entangled states. So I can compress the information and send. That was the idea behind the compression there. So, but there was another element that you mentioned of uncertainty. Suppose I were to model this on a probabilistic Turing machine, would that make me land up in a NP-hard problem? Like, would I have no way to go? This is one thing. And the other thing is, when the question of entropy, of Shannon's entropy comes to language, the usual intuition of entropy is that if I have, say, all zeros, its entropy is zero. I don't have any new information. So if I were to mix zeros and ones, the entropy increases and I have some information. But in language, if entropy increases, would the meaning survive? So would entropy and meaning have, correlations? Like, I don't usually expect entropy to increase if I want meaning.
Okay,
right.
All right. So maybe I'll try to answer those questions. I saw three ingredients in those questions. First, you talked about super dense coding and sharing entanglement. By the way, I'm not doing any of that. This is classical communication. The only things that we're sharing a priori is an understanding that this is the framework under which we're working. We're going to have distributions, but we're going to have uncertainty, and we're going to be using mechanisms to compress under this uncertainty. You asked a second question, which was computational complexity. We suppressed all of that away, and here I'm following the footsteps of Shannon, who also suppressed all computational complexity issues away for a long time, and it took 30, 40 years, depending on how you count, to actually catch up with many of these things. So we would like to understand what can be done when you ignore computational constraints, then you bring the computational constraints again. This is not to suggest that we are dismissing the issues, but just to say, well, there are issues beyond computation. We want to settle those first and then come back to those. And finally, the third question was, can you just give me a word to remind me?
The meaning and entropy.
The
Right.
meaning. Now, uncertainty slowly, I mean, yes, we will lose the concept of what something meant over time. We encounter this, and this is what leads to the fields like archaeology and so on, where people are looking at ancient texts and trying to figure out what they meant. We will, in the digital world, this has happened a few times. There are formats in which maybe my first scribe notes in the class that I took, I wrote those, and now nobody can actually read that piece of information. So over time, we will lose this, and it's somehow related to some increasing entropy in the universe, and also an increasing and an evolutionary feature associated with language. We do have to think about it, but we cannot. There are no solutions which will solve everything. Either we try to keep perpetually a notion of history, saying everything that we've ever used, we will try to enshrine those meanings. And we can do that by creating libraries and museums, but then if you expect your teenage children to find out, to know everything, what everything meant 20 years ago, you're fighting a hopeless battle. So there are evolutionary pressures which also force us to forget things that we have known in the past so that we can focus on the new things.
Thank you.
We can take one more question. We'll have a question. Madhu, go.
Are not just acting as a sender of information or a receiver of information, they're actually exchanging messages back and forth. This has been proven to be a very effective mechanism empirically as well as theoretically for communication and for for acquiring information. We have not yet found mechanisms where we can analyze them nicely and which work very well under the kinds of uncertainty that we have introduced. I would think it's probably a flaw with our ability to things, and in one of these results we actually describe this as an open question. Not that we cannot envision better mechanisms, but we just don't have any so far.